Hi, good afternoon to everyone. Welcome you all for the AICTE PRERANA scheme for preparing SC/ST students for higher education training. Okay, by Erode Sengunthar Engineering College, Tamil Nadu. In this session, you will discuss about the subject digital logic circuits. Under this subject, we will discuss about the topics counters and design a modify counters. Session handled by myself, R.Senthilkumar, Assistant Professor, Department of EEE, Electrical and Electronics Engineering, Erode Sengunthar Engineering College, Erode District, Tamil Nadu. Okay, first of all, we will need to know about what is meant by counters. Okay, a counter is a register capable of counting the number of clock pulses arriving at its input clock. Okay, so in generally we will know about the term counter. Okay, in a ticket counter, what is the purpose of ticket counter? Okay, in the ticket counter, we will know how many persons entered into the particular batch after providing a ticket. Okay, likewise, counter is a register. Okay, register is recordable. Okay, it counts how many numbers. Okay, 1 2 3 4 5 6. So 20 in the batch means 20. After counting the number 20, then other persons, the next coming persons is allowed to next batch, like that. Count is a register. It has the capability to count the numbers. In this counters in digital logic circuits, capable of counting the number of clock pulses by arriving at its clock input. For every clock pulse input, it counts the pulse. Okay. So what is the term count? Count represents the number of clock pulses arrived. Okay. Okay. On arrival of each clock pulse, the counter is incremented by 1. Okay. On arrival of every clock pulse input, it counts the value by 1. Okay. In case of, suppose this is called up counter. Okay. In case of down counter, here on arrival of each clock pulse, okay, its value is decremented by 1. Is called down counter. See the images two figures shows. First images shows positive triggering counter. Second image shows negative triggered counter. So see the difference between the two images and identify the difference in the sense clock pulse input is the difference. Okay, see the first image, clock pulse is directly given to the clock pulse input. In second image, clock pulse is given to the input of the counter through complementing to the complementing gate. Okay, so complementing gate in the sense if you give the values 1, it goes 0. Otherwise, in the sense the values give the input is 0, then the value in sent to the counter is 1. Okay, so both of the counters are same, but the types are different by clock pulse given input. Okay, positive trigger and negative trigger counters. Okay. So external clock is applied to the input clock of the counter. Okay, to count the number of clock pulses. Okay, the counters can be positive triggered or negative triggered. Based on triggering, counters can be divided into two types. One is positive triggering, another is negative triggered. Okay, based on the type, clock counters classified into two types. One is up counter, and another is down counter. Okay. Okay. So, see, counters have different bit counters. For example, it is maybe it's 1 bit counter, 2 bit counter, 3 bit counter, 4 bit, like that. So the n-bit counter has n flip-flops. Okay, and it has 2 power n distinct states of output. Suppose if the flip, for example, if it has 2-bit counter, it has 2 flip-flops. Okay, n-bit counter has n flip-flops. For each flip-flop stores 1 bit. So okay, for 2-bit flip-flop, we need 2 flip-flops, right? And it has 2 power n. 2 power n in the sense n bit is 2, therefore 2 power n is 2 power 2 is 4 states. Okay, so if you toss a coin, we maybe 2 coins tossed, we get head tail head, or tail like that. When 2 flip flops are used, to 4 different states are distinct states will arrive 0 0, maybe 0 0 or 0 1 1 0 and 1 1. Okay, suppose if it has 3, if the input is 3-bit and binary counter, it has now we need 3 flip flops and it has 2 power 3 states, in a sense 8 distinct states. Okay, so 0 0 0 0 0 1 0 1 0 0 1 1 100 101 110 111 up to 111. Okay, it is called 3-bit counter. Okay, the maximum count that the binary count can count is 2 power n minus 1. The maximum counter that the binary counter can count is 2 power n minus 1. Okay, see for 2-bit counter, 2 power n in the sense 2 power 2. Okay, 2 power 2 is 4, minus 1 is 3 different states are there. Okay, so maximum count that the binary counter count is 3th binary value. So 3th binary value is 1 1. So see 0 0 0 1 1 0 and 1 1. This is called maximum count that the binary counter can count. For example, in 2-bit binary counter, the maximum count is 2 power 2 minus 1 is equal to 3. Therefore, 1 1 in binary. Okay. After reaching the maximum count, the counter resets to 0 on arrival of next clock pulse and starts counting again. Okay. So, for 2-bit counter, the counter counts to 0 0, next 0 0 to 0 1, 1 0, 1 1, and again the counter resets to 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. Like that, the counter resets to 0 for arriving of next each clock pulse and it starts counting again and again. Okay. So count is a register that describes a series of states. Okay. Applications of counters. See, watches, clocks, alarms, web browser, refresh. Okay. After reaching the certain clock, the pulses, it goes to next state. Likewise. So it's the applications used. So you see in web browser refresh. See, it's waiting for some particular time. It counts for some particular time. Then it goes to off state or idle state. For example, if you're trying to use an ITR website, income tax return filing website, when you enters into the website through your login PAN number and password, then after login you see the top corner of the website page, there is a time setter, okay, counter. Okay, the counter starts from 20 minutes from 200. 20 minutes, 19.59, 58, 19.57, 56. After a particular state is reset to 0.00 dot colon 00. Okay, after goes to 0, the counter counts and resets to counter counts and the output works. Okay, that's the counter application is there. So in any so you students have opportunity to did and done so many competitive examinations. In that examinations also, online examinations for banking exams, competition, any type of company, TCS, Infosys examination, for each question the set a prescribed time for one question for 1 minute. Likewise, all 60 questions 60 minutes. After reaching the particular time, the counter automatically it submits. Okay, so this is the applications of counters. So the counters, there are two types of counters based on the connections. Okay, so the two types of counters are synchronous counters and asynchronous counters. What is meant by synchronous counters? When the counter is clocked such that each flip-flop in the counter is triggered at the same time. When the counter is clocked such that each flip-flop in the counter is triggered at the same time, the counter is called synchronous counter. Or that means all the flip-flops are clocked simultaneously is called synchronous counter. Okay, all the flip-flops are clocked at a time is called synchronous counter. See, for this example, suppose if we have three water tanks, through the water tank is filled with water through the pipe. All the tanks are connected with the same pipe. Okay, if 3 liters of water is passed through the pipe, each tank is filled with 1 liter. Okay, 3 tank has 1 liter. Each tank filled with 1 liter. Therefore, the 3 liter input is given to all the 3 tanks are equally filled. Is called synchronous counter. Likewise, all the flip flops are clocked simultaneously is called a synchronous counter. So the term synchronous we will known in our smartphone mobile itself. So in that your account is synchronized. What it means, if your Gmail account is synchronized in the sense all the contacts in your mobile is synchronized with that Gmail account. So if you can use that Gmail account in any mobile, okay, so you can use that contact at any time, anywhere, in any location. Okay, so like that synchronization, the data backup is synchronized in your gadget device. Okay, so what the term synchronized means connecting. Okay, at the same time. Okay, connecting data is uploaded. Okay, and downloaded can be uploaded at the same time, synchronized with your device and with the cloud saving device is known as synchronous. Okay, so likewise synchronous in the sense all the flip flops are clocked simultaneously. okay, at the same time is called synchronous counters. Okay. So the synchronous counters, another name of synchronous counter is parallel counters. Okay. So all the flip-flops trigger simultaneously, but the clock input pulses is called synchronous counters. That means its speed is high when compared to a synchronous counter because all the flip-flops are clocked simultaneously in the sense all the flip-flops produce the output at the same time. Okay. Okay. So remember, if j equal to k equal to 0, flip-flop output value maintains the output value as same. Suppose if j value and k value is equal to 1, flip-flop toggles. Okay. If j value and k value is equal to 1, if we send the clock pulse, the output toggles. Suppose if the previous output is 0, now the output is 1. Suppose the previous output is 1, now the output toggles to 0. Okay. So most counters are synchronous in computer systems because of the need of high speed. Okay. Okay. See, in synchronous counter, for example, 2-bit synchronous counter, 3-bit, 4-bit, it depends on our desired range. Okay. 2-bit synchronous binary up counter is, this image shows 2-bit synchronous binary up counter. So 2-bit, for each bit, we need each flip flop. For 2-bit, we need 2 flip flops. Okay. So each flip flop has the capabilities to store 1 bit. Okay. So JK type is used here. So JA, KA. So 2 flip flops in the sense A flip flop and B flip flop. So now the given input as JA, JP, KP. Okay. QAS output, QBS output for second flip flop, QS output for first flip flop. This is the general flip flop symbol format. Okay. Now you see figure source of two-stage synchronous counter. Clock signal is connected in parallel to clock inputs of both the flip flops. Okay, here the clock pulse input is given to the complementing flip flops. Therefore, it is negative edge triggered flip flop. Right, the clock signal is connected to in parallel to both flip flops. Right. Okay, JAK is given as high value, but that is J. That means JA and KA equal to JA equal to KA is equal to 1. Okay, so j is equal to k equal to 1. See this the side. When j is k is equal to 1, flip flop toggles. Okay, so when j k equal to 1, flip flop toggles when clock pulse is applied. See, if the clock pulse is applied, the 0 value goes to 1 and the 1 value goes to 0. This is the timing diagram of a 3-bit synchronous counter. Suppose if the 2-bit synchronous counter, if we need 3-bit synchronous counter, an additional flip flop JCKC is added. Flip flop C is added to in parallel with the next flip flop near to B flip flop. Therefore, if you see the table sequence for 3-bit synchronous counter, so see when clock pulse 0 is applied, QC, QB, QA value is equal to 0, 0, 0. When 1 is applied 0, 0, 1, then 2 applied it goes to next state 0, 1, 0. When 3 is applied goes to next succeeding state 0, 1, 1. Next 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Then again starts counts from 0, 0, 0 to 0, 1, likewise. Okay, when 3-bit counter is the sense used. So when clock pulse is applied up to 1 to 8, when the first clock pulse is applied negative edge triggering occurrence, the first the A flip flop starts toggling. Okay, so QA produces output as 1, 0 to 1. Okay, when next flip flop, when the negative edge triggering occurred of second time, QB flip flop starts toggling. When goes for next negative edge triggering, when QA flip flop negative triggering occurrence in the sense QB flip flop starts triggering. After receiving the negative triggering of QB flip flop, QC flip flop starts triggering. Likewise, the timing diagram is drawn. In this slide shows 4-bit synchronous binary up counter. The figure shows the binary up counter of 4-bit synchronous counter. So see what is up counter. So up counter in the sense QA output is given to JPKB. QB output is given to JCKC. QC output is given to JDKD. Like that up counter is drawn here. What is synchronous counter? Synchronous counter means all the clock pulses are clocked by a single simultaneously. Okay, that is called synchronous counter. What is 4-bit? 4-bit in the sense we need 4 flip flops. So for 4-bit we are using 4-bit flip flops. For synchronous counter, all the flip flops are clocked simultaneously. For binary up counter, JA KA value is given as high. After first flip flop, the output goes to second flip flop input. The second flip flop output goes to third flip flop input. Flip flop output goes to fourth flip flop input. by combining the first flip-flop and second flip-flop output with the help of by combining this both outputs, and it's given to the next flip-flop, that is called C flip-flop. By combining the C flip-flop output and all the flip-flop outputs given to the 3-input gate, then it gives to the fourth flip-flop input. This is called connections of 4-bit synchronous binary up counter. See this logic diagram of 4-bit binary up counter. So when the first clock pulse of negative trigger occurs, first flip-flop toggles, okay, 0 to 1. When the first flip-flop output, see, first flip-flop QA, first negative edge triggering occurs, QB flip-flop toggles 0 to 1. When the negative edge triggering of QB flip-flop occurs, QC flip-flop toggles 0 to 1. When the negative trigger of QC flip-flop occur, QD flip-flop toggles. Okay. When see the first QA flip-flop output. When the negative edge triggering of next occurrence occur, QB flip-flops toggles from 1 to 0. Like this manner, the cycle continues and it counts from 0 to 111 and again resets to 0 to 000 to 111. Okay, next synchronous up down counters, synchronous down counters, synchronous up down counters. In this image, see, same 3-bit counter is used, JKA, KB, KB, JC, KC. Okay, so see the J value and K value given as input as high logic 1. All the flip flops are clocked simultaneously through the clock pulses. When J K value is equal to 1, see, QA output and QA bar output. If we need up counter, we need to use the QA output, QB output, and QC output. Suppose if we need down counter, we can use the QA bar, QB bar, and QC bar output. So by controlling the up down counters, we are using a mode up counters mode with the help of NOT gates and AND gates and OR gates. Like this connection, we can done the synchronous up down parallel counters. So when it is up counters, it counts from 000 to 001, 010 up to 111 and the counter is to 000. When it is down counted, counts the value by down decrementing by 111 to 000 and again resets to 111 to 000. Okay. Figure shows the timing diagram of the up counter and down counter. When the up counter is enabled, the first image timing diagram is operated. When down counter is enabled, second timing diagram is get us output. Okay, next, second type of counters is called asynchronous counter. So what's asynchronous counter means all the flip flops are clocked simultaneously is called synchronous counter. All the flip flops are not clocked simultaneously is called asynchronous counters. See, in asynchronous counters, the synchronous counter has other name as parallel counter. Asynchronous counter has other name as binary ripple counter or asynchronous counter. It consists of a series connection, that's parallel connection. Here it is series connection of complementing flip flops with the output of each flip flop connected to the clock input of the next higher order flip flop. See, here the output of each flip flop is connected to the next clock pulse of the higher order flip flop, next flip flop. Okay, the second flip flop output is connected to the output. Second flip flop output is connected to the clock pulse of the next flip flop input. This is called asynchronous counter. See, in this, when the first flip flop output is toggled, then it goes to the second flip flop clock pulse like that. All the tanks are not filled simultaneously. It's called asynchronous counter. See, for example, if the first tank water is filled, then after after completing the first tank water level, then it goes to the second tank of water through a pipe at the top. Okay, when it fills the second tank water, after completing the top level, then it goes to the third tank. Likewise, asynchronous counter was operator. The flip flop holding the LSB receives the incoming clock pulses. The flip flop holding the least significant bit receives the incoming clock pulses. Okay. See, another asynchronous ripple counter. Asynchronous counters are ripple counters. Okay. JK flip flop is used. So this is the 4-bit asynchronous ripple counter. Okay. See, 4-bit in the sense 00002 0001 0010 0011 up to 1111. So totally 16 counts, right? Okay, next asynchronous counter. So each flip-flop output drives the clock input of the next higher order flip-flop. Okay, as I stated that already, each flip-flop output is given to the clock pulse of the next higher order flip-flop. Okay, so flip-flop does not change states in the exact synchronism with the upright clock pulse. When the clock pulse is upright, we did not get the output from all the flip-flops. Okay, so there is a delay between the response of every successive flip-flops. Therefore, the speed is low when compared to synchronous counter. The asynchronous counter is low because of series connection of flip-flops. Okay. Okay. Next, this is the output waveforms of 3-bit asynchronous counter. So when it is counted asynchronous, the output are same as synchronous counter, but the connections is different. Okay, but the connection is different. This is the logic diagram of 3-input asynchronous counter with negative edge recurring flip-flops. So if it is asynchronous counter, what we have to do is we for 3-stage counter we need 3 flip-flops. Therefore, we draw 3 A, B, C, J, A, K, A, K, B, K, B, J, C, K, C. Okay. So first flip-flop input is given as high. J A value, K A value is equal to high. Okay. Okay. Now see, all the flip-flop input is given as high. Okay. The first flip-flop output is given to second flip-flop clock pulse. First flip-flop output is given to second flip-flop clock input is called as asynchronous counters. Okay, what is negative triggering? The clock pulse input is complementing clock pulse input. Okay, that is called negative triggering flip flops. So this diagram shows the 3-bit negative edge triggered counter. Okay. Okay. See, what is asynchronous? What is the difference between synchronous counters and asynchronous counter? That is, what is the difference between asynchronous or ripple counter and synchronous or parallel counter, asynchronous ripple counter, or parallel counter? Okay, asynchronous counter. In this type of counter, flip flops are connected in such a way that output of first flip flop drives the clocks of the next flip flop. Okay, the output of first flip flop drives the clock for the second flip flop. This is called asynchronous counter. In this type of counter, there is no connection between the output of first flip-flop and the clock input of the next order flip-flop. Okay, all the flip-flops are not clocked simultaneously is called asynchronous counters. All the flip-flops are clocked simultaneously is called synchronous counter. Here the logic circuit is very simple even for more number of states in where asynchronous counter. Okay, in synchronous counter, logic circuit is somewhat complex because as large number of states increases, number of states increases. Right. Okay. Main drawbacks of this counter is low speed. It reaches when it reaches the last flip flop. Synchronous counter has high speed. Most advantages of this flip flop. So these flip flops are preferred when number of flip flop increases in given design. Okay, because of the high is used for high speed counters. Okay, so it's a difference between synchronous counters and asynchronous. So main difference is all the flip flops are clock simultaneously is called synchronous counter. All the flip flops are not clock simultaneously is called asynchronous counters. Okay. Next, asynchronous up down counter. Like synchronous up down counter, there is asynchronous up down counter. So for up counter, so this is the basic image sources combination circuit where the output of previous flip flop is given to Q is called as up counter. Where the output of previous flip flop is given to Q bar is called down counter. So the mode M is used for mode control. When it is 0, it goes for up counter. It's good. One it goes for down counter. The output given so the combination circuit gives the output. Okay. Okay, but for use K-map simplification, we can get the logic diagram and uses the here the circuit uses 3-bit synchronous up-down counter. When the mode is 1, it counts the values from 000 to 111. When the mode is 0, it counts the values from 111 to 000. When the mode is 1, it acts as up counter. When the mode is 0, to acts as a down counter. Okay. So the timing diagram for 3-bit up counter. Okay, so the same as synchronous up counter. So it counts the values from 000 to 111. Okay, this is the timing diagram of 3-bit down counters. It's just complementing the each flip-flop output. Okay, QA, see the QA output as 0 1 0 1. So see here the image here. When it's used for down counter, we used the previous flip-flop output to Q bar. Okay, so we are here complementing the QA output. So if the QA output is 0, the QA bar is 1, like that. Okay, so QA bar, QB bar, QC bar. So it counts the value down. Okay, triple zero, triple one, double one zero, up to triple zero, and again triple one, double one zero. Again it counts down. Okay, like that. These counters are operating. Next, asynchronous counter or ripple down counter. Okay, so see the images of 4-bit asynchronous counters here. Clock pulse, first clock pulse is given, then the output of the QA complementing output is given to the next higher order flip flops of each flip flop as same. All the flip flop inputs are cooperated connected to high value. So this is called 4-bit asynchronous down counters. So JK flip flop is used therefore 4-bit asynchronous JK down counter. Okay, next 2-bit asynchronous counter. Okay, so asynchronous counter in the sense first flip flop is given to the next flip flop clock pulse. Okay, so 2-bit flip flop is used because of 2-bit asynchronous counter. So JAKA, JBKB, two flip flops are used. I values are given to JAKA and JBKB values. This timing diagrams for 2-bit asynchronous counter shown. Okay, so 0 it starts count from 0 0 0 1 1 0 1 1. Okay, because of 2-bit counter it has 4 states. Okay, 0 0 2 1 1. So summary, binary counters can be ripple counters or synchronous counters. Okay, ripple counters use flip-flop output as flip-flop triggers. Synchronous counters are controlled by a clock pulses, right? Okay. So, see our first slide. Our topic was counters. Okay, session was counters, and second topic of design a modify synchronous up counters using a particular JK flip flop. Okay, so we are moving to next topic as modulus counters. Okay, in this modulus counter, we are designing a particular modify counter synchronous up counter using JK flip flops. Okay. So design a modify counter, design a modify synchronous up counter using JK flip flop. So follow for this, we need to follow the following steps. Step 1, the 5 steps are there. Step 1, determine the number of flip flops needed. Okay, we have to determine the number of flip flops needed. Step 2, type of flip flops to be used. Step 2 is type of flip flop to be used. What type of flip flop we can use? First step is to determine the number of flip flops. Second step is to find the type of flip flop. Third step is to draw the excitation table for the JK flip flop. By using this JK flip flop excitation table, we need to draw the excitation table for the particular counters. Next step 4 is K map simplification. Okay, by drawing this K map simplification, we can obtain the Boolean equation. By using this Boolean equation, we can see the logic diagram and the timing diagram. Okay. Okay. So modify counter. Determine the number of flip flops needed. This is the first step. Okay, flip flop requires there is a formula for finding the number of flip flops for a particular mod n counters. So see 2 power n greater than or equal to 1. Okay, here mod 5, hence capital N is equal to 5. So mod 5 counters is capital N. Okay, so mod 5 counter therefore capital N is equal to 5. Suppose if it's mod 10 counter, capital N is equal to 10. Okay, mod n counter, so that is mod capital N counter. Okay, so for mod 5 counter, capital N is equal to 5. Small n we need to find out by using this relationship. Okay, therefore 2 power n greater than or is equal to 5, because 2 power n greater than or equal to mod 5 value is 5, therefore 2 power n greater than or equal to 5. So by using substituting the n is equal to 1, therefore 2 power 1 2 power 1 is equal to, therefore 2 power n is 2 power 2 is 1 equal to 1, therefore the output is 2. 2 is greater than or equal to 5, no. 2 is less than 5, therefore 2 power n is equal to 2 is substituted. 2 power 2 is 4, 4 is greater than or equal to 5, no. Wrong, therefore n substitute n is equal to 3, therefore 2 over 3 is equal to 8, 8 is greater than or equal to 5, yes, it is correct. Therefore n is equal to small n is equal to 3. Here the capital n is equal to 3 is wrong. Small n is equal to 3. Therefore, number of flip-flops required are 3. 3 flip-flops are required because of small n equal to 3. Okay, next step 2. Step 2, to find out the types of flip-flop to be used. What are the type of flip-flops to be used? Here the flip-flop type you can use is JK flip-flop, because in question itself they are saying that designing modified synchrons subcounter by using a JK flip-flops only. So the type of flip-flop to be used is JK flip-flop. Okay. Okay. Next step 3. What step 3? Determine the excitation table for the JK flip-flop, and also determine the excitation table of the particular counters. Okay. See, this is the excitation table for the JK flip-flop. If J for Qn present state value 0, next state value is 0. So 0 0, the what is the value of JK? For 0 1, what is the value of JK? For 1 0, what is the value of JK? So it's 0x, 1x, and the x1. Okay. Now we can derive the excitation table for the counter using the above excitation table for particular JK type flip-flop. So next step is to determine the excitation table for the particular mod 5 counter. So the excitation table consists of present stable. See, the excitation table for the flip-flop consists of present state, next state, and the JK inputs. See, the excitation table for particular counter, mod 5 counter, consists of present state, next state, and flip-flop inputs given. So the present state gives QB is equal to 0 0 0 2. What about next state? Suppose if the present state is 0, next state is 1. Suppose the present state is 1, next state is 1 0. Suppose the present state is 1 0, next state is 1 1. Like that, up to triple 1 and triple 0, the cycle continues. Triple 0 to triple 1, triple 1 to triple 0, like that. Okay. Okay, because of mod 5 counters we are used, therefore see the next state 000 to 001, 001 is goes to next state 010. For 010 it goes to next state 011. For 011, so 011 is the last bit count, therefore it counts it's called the counter four different distinct states. Therefore after completing the 011 it goes to next state as 100. Okay, so for mod 5 counter, value of 5 is equal to 101. Before 5 values, 4 binary values 4 is 100. So after completing the value 100, it goes to next state as 000. Again 000. So all the states are 0. For 6%, for 5, 6, 7%, there is no next state. So therefore, it has don't care x, 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 x. Okay, so for mod 5 counter goes 000 to 001, 001 to 010, 010 to 011, 011 to 111. This is the mod 5 counters percentage next state table. Okay, see now we have to draw the flip-flop circuit diagram. We need flip-flop inputs and output equations. So the flip-flop, there are 3 flip-flops are used here. Therefore, JC, KC, JB, KB, JA, GA. Because of 3 flip-flops, 3 different areas, 3 different areas are used. Okay, what is present state is QC. Next state is QC. Therefore, JK values. But see the first row. Present state Qn is 0. Next state Qn person is 0. Therefore, J value, K value is 0x. See the J value, K value as 0 0. JC value as 0. KC value as x. Okay. When the QB value and QB plus 1 is 0. So again you are using actually JC value is 0 and KC value is 1. X. Sorry, the term is wrong. Okay, no problem. You can correct it. So see the next column QB as 0. QB plus 1 next state as 0 0. So for the present state 0, next state as 0. JB value as 0. KB value as x. See QA value is equal to 0 in first row. QA plus 1 equal to 1. So see present state is 0, next state is 1. J value is 1, K value is x. So J value is 1, K value is x. Like this, you are drawing the determining the excitation table for all the values in present state and next state table from this table. Okay. So after obtaining this flip-flop input, we need to find out the Boolean value to draw the circuit diagram. Okay. For Boolean value, for deriving the Boolean value, we are using the KMF simplification. For this KMF simplification, for deriving the values. See this JC input as triple double x double x one double x. Okay. So using QB QA. Okay, 001 010 010 011. Okay, uh, JC. So JC value is written as KC value and KC value is written as JC value. So see the KC value 01 double X 0 triple X. Okay, so here 01. Okay, 01 double X 0 triple X. Okay, we can see for KC value, JP value. See the JP value is 01 double X 0 triple X. Okay, JP value is 01 double X 0 triple X. So grouping these cells, okay. See in JCS we can group as QP. JC is equal to QB QA because QB QA is common to both the rows. Likewise, we are deriving the KC value. So here grouping can be formed together. Therefore, KC is equal to 1 because of all the cells are grouped together. So for for JP, see the first row and second row are grouped, first column, second column are grouped. Therefore, the common in first and second column is 0. That is QB bar. See the second first column, first and second row for both the common value is nothing. Okay, what's the common? QC is equal to QC. See here, for comparing the both columns, we are obtaining the QB as common in this row. Nothing is common. Okay, so therefore the JP value is equal to Q. So all the groupings are grouped together. Therefore, JP value is equal to QA. This is the KMF for KB mapping. Okay, here x1, x1, x. Okay, the common term is QA, KB, KC, KD is equal to QA. Likewise, we are drawing the JA, KA, JB, KC, JC, KC values. By using this Boolean function in the obtained JA, JB, KB, JC, JC, KC values, we are deriving the, we can exactly draw the handle the laboratory experiments. Okay, see here QA bar, QB bar, QC bar is kept as transformer oil expansion. During the oil expansion, then it was evaporated during this tubes. Okay, so JAK, JBKP, JCKC, QQ bar, QA, QB bar, QC bar. Okay. See here, we are using the asynchronous down counters when you are using. Therefore, the first clock pulse output is given to the second input of clock. So second asynchronous up counter, down counter. What's the heading? What's the heading in the sense? What's the heading? Synchronous up counter using JK flip flop. Sorry, see, we are using synchronous up counters. Therefore, QE output is given to QB output is given to QC because it is synchronous up counters. Okay, QC value is given by one QA input, that is QA input, and the QC value is considered as R.Senthilkumar. Okay, as monitoring. Okay, this way the large ARM was operated. So The first flip-flop output is directly given to the second flip-flop input. The second flip-flop output and the high clock pulse, sorry, and the salt order is used for delivering the output. Therefore, the motor is operated with normal. Okay, this is the simple logic diagram for mod 5 counters. This is the diagram for mod 5 counter. It counts 0, 1, 2, 3, 4 binary values. See 0, 0, 0, 2, 0, 0, 1, 0, 1, 0, 0, 0, 0, 100, 101. Likewise, it starts counting and repeating again. 0, 0, 1, 2, 0, 1, 0, 0, 1, 1, 0, 1, 1, 100, and triple zero. Again, it starts counting the same count triple again. Triple zero to triple zero. It, finally, I am very glad and thankful to say thank you for giving an opportunity to remind the real subjects and hand over to you. From next year, next time onwards, we will discuss the great coaching top class in this from this session. Thank you very much. Thank you so much, all. Thank you.